Hello guys. Just before we get back to the lead code video, I want to tell you that I'm making natural language processing videos. There are quite a lot of things to talk about, like training encoder-based models such as BERT, Robert IA, or even things like Modern BERT, or about concepts like multi-GPU training or curriculum learning. So I just hope you're patient. Meanwhile, let's continue with today's topic of lead code, and the problem is about intersection of two linked lists. So we are given this two heads of singly linked lists, head A and head B, and we want to find if there is intersection and what is the node at which these two linked lists intersect. If there is no intersection, we do want to return null in that case. So this is an example in the plot here. You can see there are two linked lists. They have an intersection at C1, so we want to return the C1 node. On your right, you can see that we have a function which takes in head A and head B. Those are our two linked lists, and we're going to solve this problem in three different ways. The first one is a naive approach. The second one, we are going to use a hashed method. And finally, in the third one, we are going to use two-pointer method to solve this exact same problem. So let's get back. Let me just copy and paste our naive approach from my list of solutions. So let me paste that. So yeah, this is the naive approach, and as you can see, there is a nested loop. So what I'm doing is here, I am first selecting head A as an anchor, and inside the loop, what I'm doing is using head B and initializing temp B with the head B, and I'm iterating to different values of temp B. Basically, I'm traversing this second linked list using this loop. So first I'm checking if head A, which is the anchored node, is same as the node at the second linked list. If they are same, then I want to return this head A because that is the point where we are intersecting. But if that's not the case, then what I'm doing is traversing the second linked list. You can see here I'm initializing temp B with the next node, and this loop runs as long as, you know, basically either the second linked list completes, or we find a common intersection. But if we don't find any intersection, then what happens is that we update the anchoring or the first linked list. As you can see here, I'm basically traversing the first linked list and then looping it again, and this is a very naive approach. If we don't have any intersection at the end, I want to return none. That's what I'm doing here, and this is a naive approach. It's probably the slowest approach as well. So let me run this. So it runs, that's great, and let's submit it. Well, as you can see that our time has exceeded, probably because the constraints are pretty high. Let me see. So you can see M and N are the number of linked list nodes in list A and list B, and they can go pretty high. So the complexity of our code is of n squared, and n squared of this exponential number is pretty big. So yeah, so that means this is quite inefficient and we have run out of time. So let's use hashed method. Hashed method is even simpler, I think, than what we did here, because it's, let me see. Okay, see, this is the solution where we're using hashed method. So in this, what we're doing is that we first initialized a set variable called scene nodes. This set will have all the nodes that we have seen so far. So first of all, what I'm going to do is loop or traverse completely the first linked list, which is head A. So in head A, as I traverse, what I'm doing is adding those nodes in the scene nodes set. You can see I am adding the nodes and I'm traversing one step at a time, adding the node, and I'm done with this loop once the head A is complete, that linked list is complete. And finally, then after that, I'm traversing in the head B, or our second linked list. In the second linked list, what I'm doing is that I'm checking if there's an intersection. So if the node in the second linked list is same, has been found in the C node, then it means that it is the intersection. So we're returning the head B in that case. If it's not the case, then I'm traversing to the next node, and then here I'm again checking if this new node has been found, is already there in the scene nodes or not. And if I cannot find any intersection, I have to return none, and that's what I'm doing here. So let me run this code. It should run, I hope so. It does, and let me submit it. The complexity of this code is much less because as you can see, it's not exceeded our time limit. Still very slow, it's still at very slow, but it does the job. It basically didn't go with x time exceed. And the complexity of code is if head A had m, sorry, what's the term they used, let me check back. If list A has n elements and list B has n elements, then our complexity of our code is O of m plus n. It's not a nested loop. That's something that's important. And finally, let's solve this using two-pointer method. So let me pull up my solution here. Let me paste it. So this is our solution. In this case, what I'm doing here is that I'm first checking if either of those, head A or head B, is none. If either one of those is none, then obviously there is no intersection, so I want to return none. If that's not the case, then what I'm doing is initializing these two variables PA and PB with heads of the two linked list. And I have a one while loop, and I'm checking this while loop runs until these two variables that I just initialized, PA and PB, are not same. They will keep running until that. So inside the loop, what I'm doing is I'm simply traversing actually. So if you see this first line of code, what I'm doing is traversing the first linked list. I'm just setting this PA with the next node in the PA if PA exists. So if PA is null, or if I've already reached the end of the linked list, then I want to initialize PA at the start of the second linked list. So I'm switching list here. If PA is not null or none, that means that the first linked list hasn't ended, then I want to traverse to the next node. But if it's at the end, I want to switch it to the head of the second linked list. Similarly, for PB, I'm doing the same. I'm traversing PB to the next node if PB it has not ended. It's not the end node. Then I'm just traversing to the next node. But if I'm at the end, then what I'm doing is switching from the second linked list to the start of the first linked list. Now the idea here is that both PA and PB traverses the same number of nodes. So let me give you a visual representation of what's happening here. So let us just consider that in the first linked list, let's say there are two different nodes here which are independent or which is not a part of the intersection. Let's just say that there are 8 different such nodes. In this case, A is 2 because there are 2 nodes. Similarly, B be the number of nodes in the second linked list that is not part of the intersection. So in this case, B is 4. And similarly, C be the number of intersecting number of nodes in the intersection of those two linked lists. So in this case, C is also 2 because there are 2 nodes, right? Now, the idea is that, let me just put a text here. The idea is that it's A plus C, that's the end of the first linked list. Then it starts again, so from B, again C. So this is the number of node it has traversed when it starts from the first linked list. Similarly, if it starts with the second linked list, it is going to travel B plus C, and then it's going to switch the linked list, so it's going to go to A and then to C. So if you've noticed that the number of traversal of nodes are equal in both cases, which means that they will reach at the end of the linked list at the same time. See, A plus C plus B plus C is same as, if you just rearrange those numbers, then it's the same. Basically, they are, what I mean to mean is they are equal. That's great, but what is the mathematical proof that those two, PA and PB, which is our iterating node, will actually come to a common node, this particular intersecting node? What's the proof, right? So the proof is that, then let's just cancel this C, right? Let's just subtract C from both left hand side and right hand side. At that instant, both PA and PB, which is our iterating nodes, will be at this intersecting node. So this is the proof that we are definitely going to reach the common node, intersecting node, if they intersect. But if they don't intersect, then we are going to reach the end of the node at the same time. That's what that's what we have seen, right? So that is the proof that they're going to intersect. So let's just run this code. Okay, some sort of network issue is there. Let me just refresh. I think I have an internet issue. Let's run it. Okay, it does run. Let's submit it. It runs great. And now the complexity of this code is also of m plus n in this case. So that's the solution. Thank you guys for listening to me, and have a good one.